non-local energies in the class of polytopes.
Okay. Thank you, Ethan, for the introduction, and to you, Leah and Stanley, for organizing this mini workshop and for inviting me, and to all of you in the audience for being here this afternoon. And I guess now the only time zone is afternoon for everyone, so I can just say afternoon. Okay, so today I would like to talk to you about a couple of projects, ongoing projects in collaboration with Marco and Ethan. And in case you have seen also the talk of Ethan's, now I'm going to do something from a different point of view, so you don't see the same talk twice. Okay, so I'm going to start with one of the two projects that is about non-local energies on polygons. Start we consider a very well-known non-local energy, that is the Riss energy, that is generalization of the important Coulombic potential that is very important in physics because it's related to the stability of matter. In particular, in the physics literature, this sort of energies are used in order to understand what is the shape of atoms that contain themselves. And therefore, a problem in this business is to maximize this energy. Usually in physics, this energy is with a minus sign, so you minimize it, but mathematically we get rid of the minus sign and we maximize it, because if you want to consider the minimization of this energy, this is trivial, you just get things that scatter to infinity together. What is important is to maximize it with a fixed mass constraint. And this problem, despite it has been known by physicists what the solution was or was expected to be, was solved by Lieb in '77, and he showed that the only solution to this problem, regardless of the mass, are balls. And he proved it by using symmetric rearrangements. Well, once you know what are the maximizers, the solution of your problems, another question that is important in order to understand the landscape of this energy are critical points. So a natural question is to ask if there are any other critical points rather than balls, because critical points can lead to local minimizers. Of course, you have to give a meaning what does it mean to be critical, so you have to introduce variations, and these are natural, so you modify your objects by using diffeomorphism. So one parameter family of diffeomorphism, that is the density when time the first variable is 0, and that is moved in the other two, in the other variables. And what you do is that you follow the evolution of your set that you fix up initially, and you compute the derivative of your energy along this one parameter family of sets. And if you do computations, this is what you get. What you get is an integral over the boundary of this object that I'm now going to introduce. So you have the last one here, that is the normal to the boundary of your set. You have the initial velocity of your family of diffeomorphisms, this capital X, and then you have this other function, V of V, that is what is called the potential. And this is just one of the two integrals. Okay, so the question is, okay, now that we have a definition of what it means to be critical point, the question is, if you have objects for which this quantity vanishes. Of course, vanishes is not precisely what we want to do, because we want to keep the mass constraint, because we have the mass constraint in the problem, and we want to keep it at least as first order, because we consider first variation. And this maintaining the volume constraint at first order is equivalent to asking the velocity field to have 0 mean on the boundary. Heuristically, the amount of mass that goes outside is the same that comes inside. And so at first order, you maintain the volume. So this is the question. So if you have a set for which this integral is 0 for every phi with 0 average, phi is x dot new, is your set something special or not? And the fact is that you see here, this implies that the potential, the function VE, is constant on the boundary. Because it is zero, it's orthogonal to the set of functions that are with zero average, so it has to be constant. So the question is, if you have a set for which this function is constant on the boundary, can you say something about the set? Yes, you can. And you can prove that sets are balls. And this has been proven by several authors with different techniques. Here, just a small list. But the bottom line is that maximizing the Ritz potential, the Ritz energy, with a mass constraint, not only gives you that the only maximizers are balls, but also that the only critical points are balls. So basically, the energy landscape is well understood. Okay, so what we wanted to understand was to consider this energy, but not in the class of all possible shapes, but in a restricted class. So still with the mass constraint, but in the class of polyhedral sets. And this can be motivated in two ways. One is to listen to the second part. The reason being that this first part came chronologically after, but I prefer that to present it in this reverse order. And the second one is that maybe you want to model something physically for which you want to be polyhedral. Okay, so if you want just to ask your set to be polyhedral and you want to maximize it, well, you do not have any solution. The reason being that you know that if we drop the constraint to be polyhedral, the solution is a ball. And if you just let your polyhedral set to be whatever, you will have a minimizing sequence that will approximate the ball with polyhedral sets. So you approximate an energy that you cannot reach with any polyhedral set. What you can do is to constrain the polyhedral sets to be in an even restricted class. In particular, if you constrain the number of faces, vertices, and edges. Of course, in general dimension, this is difficult because there are too many variables. In particular, if you go in dimension higher than 3, at least my geometric intuition, I have no idea exactly what happens. But at least in dimension 2 and 3, maybe this will be approachable. And what we did was to start with dimension 2, where polytopes are polygons. And the only thing that you can constrain in dimension 2 are the number of sides. So what we consider is the maximization of the Ritz energy with volume constraint in the class of angles, when n is the number of sides. Of course, fixing the number of sides is equivalent of fixing the maximum number of sides, because again, your shape wants to be a ball, a sphere, a circle, because you are in dimension 2. So you will try to fulfill this constraint on the number of sides. Okay. What we did was to consider a generalization of Ritz energies. So let me just go back 1 second to this slide. So you can see this integrand, so 1 over x minus y to the alpha, as a particular case of this class of non-local energies. So something that is given by kernel potential that depends on the distance between points. Of course, you can consider something that is more general, depends on also the direction or general points, but that is level of difficulty higher. And what we ask about this potential is to be a generalization of the Ritz energy. So something that is strictly decreasing, something that is of class C1, and that satisfies this assumption, integrability assumption. So let me comment on these 3 requirements. So the last one is to have the energy to be finite. If you don't ask this, the energy is infinite, so there is nothing to ask. But what about the other 2 assumptions? So class C1 is to make computations easier. Of course, you can drop a bit the regularity, but basically the fact is that it's just a technical game to recover the same computations. So we prefer like to ask this C1 and then to say, okay, if you want to have a kernel that is a bit less regular, you can do it, but do the computations. Strictly decreasing is something that is usually expected by these sort of kernels, strictly because if something is not strictly decreasing, you can lose uniqueness of your maximizers. And of course, another thing that is interesting is that here we're asking everything to be non-negative. There might be situation, for instance, some sort of Lennard-Jones potentials for which the kernel becomes negative in a region, but asymptotically zero. That might be interesting to investigate. But of course, that will be completely different because the heuristic behind is very different, right? Okay. So this is the non-local energy that we consider. And again, we pose this problem. So how to maximize these non-local energies with a mass constraint and in the class of polygons, n-gons, with the constraint on the number of sites. So this problem was basically solved for triangles and fourgons by Paul-Sego in 1951. I say basically solved because they consider a particular potential and their proof is a description of what to do. But they were smart guys, and we check that is true. I mean, if you do the computation that they say they leads to a solution, this is exactly what happens. And the proof is based on a sequence of standard symmetrization. So you start with a shape, and you do a first standard symmetrization, and you show that this operation increases your energy. And then you keep doing these operations. There is a recipe to say, okay, what is next one? And this sequence will converge to a regular triangle or a regular fourgon square. And of course, this will be demaximized because if something is not regular, you can do some standard symmetrization and make it more symmetric and increase the energy. Of course, the proof was for triangles and squares. The reason being that this technique of standard symmetrization does not work very well when you have more than 5 sides. The reason being that you want to stay within the class of polygons with this number of sides, and if you have polygons with 5 or more sides, standard symmetrization might increase the number of sides. And this is something that you cannot control. But it is conjectured that the same result holds for any number of sides. And this conjecture is still open, but don't worry, we are working on that. Okay, so this is for the first part, so how to maximize it. And then the same question as before. So now that we know for triangles and squares that those are the only maximizers, what about other critical points? Of course, again, here we have to understand what does it mean to be critical. So of course, we have to preserve the area, but not only that. We have to preserve the area and to stay in the class. So we want our variation to preserve our object to be a polygon. So we cannot just move one side as we wish. We have to preserve the fact that sides are segments. So one possible way to do it is to run the same computations as before. And to write this integral and then write a lot of conditions on what this initial velocity capital X has to be for this variation to preserve polygonality. But this is too involved because, well, if you think about it, variations that preserve the fact that something is a polygon, well, what you do is you just have n vertices, you move n minus 1 vertices as you wish, and then the last one, you're forced to move it in one direction to preserve the area constraint. And then you just connect them with the segments. And this is how you preserve also the fact to be a polygon. And our claim that is the back of our minds, and we prove in next paper, is that all these variations, all these possible variations, can be generated by two simple movements that we call sliding and tilting, that are these ones. So sliding, you take your polygon, you take your favorite side, so this one on top, it should be right, okay? And what you do is that you consider the prolongation of the lines of the edges and sides, and you slide this side along the normal direction. If you do that, this is what you obtain. You just move this side up or down. This is called sliding. The name is okay, justified. Note that this one is not volume preserving, right? The other movement is tilting. So again, you take your favorite side, you consider the prolongation of the sides of the adjacent ones, you pick the midpoint, and you rotate that side around that midpoint. And this is what you obtain. And this variation is volume preserving at the first order because you rotate around the midpoint. If you rotate around another point, it's no, but yes. And our claim is that, okay, all these possible volume preserving and polygonality preserving variations are basically a combination of these two. So if you write the condition, criticality condition with respect to those variations, that can be written in terms of these ones, or better, if that is 0, also these two are 0, and vice versa. So what are these criticality conditions? So for sliding, is basically this, is that the average of the potential on each side is the same. Whereas for tilting, this is a bit different. So you have the potential weighted by the distance from the midpoint. And if you tilt it, you have two pieces, the one on the left and the one on the right, the one that goes down, the one that goes up, and these have to be the same if weighted with the potential. And the question is, therefore, this one. So suppose that you have an angle with n is equal to 3 or 4 that satisfies these two criticality conditions. Can you say that it's regular? Yes, you can. And we proved it. And the idea is this one. I just described it with a couple of pictures. So take something that is not critical, but satisfies these two criticality conditions. Well, the idea is that you want to find a variation that increases the energy. And then you want to write that variation, and then you want to prove that that variation implies that sliding and or tilting cannot be 0. So a contradiction. Okay, so for triangles it's easy. You have this triangle. How do you make it more symmetric? Well, you take this, for instance, this vertex here, and you slide it parallel to the other side. If you do this, you get a variation that heuristically will increase the energy because the mass will come closer together, and the closer the mass is, the higher the energy is, and you get your contradiction. You do this for all vertices, and you end up with a regular triangle. For quadrilateral, you do something similar at the first step. So in order to make this quadrilateral more symmetric, you take these two vertices and you slide them in a smart way. So you slide them to a direction that is parallel to the other diagonal. If you do that, and that is a tricky part of what we did, you can show that you increase the energy. So this implies that your object must be a rhombus. How to do next step? So you take your one side, you take the median of that one, and by using a symmetrization argument, you show that your object must be a rectangle, and then for a rectangle, you go to a square by using symmetrization with respect to a bisector. Bisector. Okay. So this is in one slide with a couple of pictures what we did. Of course, you have to do everything quantitatively, so there are computations. Okay. And what we are currently doing is, of course, to try to extend this proof to the case of more size. And of course, this will also imply that we prove that also the only maximizer will be the regular angles. and to consider more general functional, non-local functions with the comments that I made before. And of course, also to go to 3 dimensions, because also that is something that may be tackled by limiting some number of sites. Okay. So in the last 5 minutes, I'm going to talk about the, yes. And of course, if you're interested in sort of methods, there are a lot of people who are working in similar things with different functional, and I suggest you to read the papers because they're really inspiring for techniques and ideas. Okay. So for the second part, we're going to talk about non-local anisotropic isoperimetric problem that chronologically came first and then was the inspiration for doing this work that I just presented. Okay. So let's consider this isoperimetric problem that is coupling a perimeter term with a non-local energy, the Ritz energy. And interested in this comes from a lot of physical models. I'm not going to even call any of them because I will have to spend 5 minutes just to recall names. But the idea is that in this sort of models, what is interesting, then there is a competition between these two terms. So the perimeter with a mass constraint is minimized by the ball, whereas we just saw that the non-local energy is maximized by the ball. So you have an object that is candidate for two opposite maximization and minimization problems, and you have a parameter, this gamma, in front of the non-local energy that measures the strength of one term with respect to the other. And you are interested in minimizing this function. What is known, and now I make just a summary of tons of results, is that for small values of gamma, you have minimizer and you know exactly what it is, that is the ball. And here is strictly less than this value, because if it was also equal and there was the maximum, we will know everything. You know that you have a solution for a value that may be larger than this one, and that for larger values, but for a stricter range of exponents alpha, that are the exponent in the Ritz potential, you have non-existence. And what is expected is that all these 3 values, they agree. So you do have a solution that is the ball, and that's the only solution until you have a solution. This is ultra difficult problem. The fact is that heuristically, if you put the exponent alpha is equal to 0, the second term is constant, is just the volume squared, and you just have the perimeter for which you know that the solution is the ball. And therefore, this kind of conjecture is known for small value of alphas by using this argument. So again, the question is, okay, what happens is here, instead of the perimeter, we take some anisotropic perimeter. Because here is different. Now, the first term is minimized by a shape, but is not the one that maximizes the second one. So the question is, what happens now? And what happens has been proved by Rustum, Ihsan, and Robin recently, is that you have a similar situation for small values of gamma. So you know that for small values of gamma, you have a solution, whereas for larger values of gamma, you don't have it, but for the same range of exponents alpha. And the question is the bush shape, so the minimizer of the anisotropic perimeter, a minimum for small values of gamma? Well, it depends. The answer is no, if your anisotropy is uniformly elliptic. That cannot be a minimizer. Yes, a minimizer. And then the question is, okay, what about other classes of anisotropies? For instance, if you consider crystalline anisotropies, can you say that the bush shape is a minimizer for small values of gamma? And the answer is yes, with a couple of additional assumptions. That is, okay, in all dimensions for all ranges of alphas, but with a small restriction on the crystalline anisotropies. That is, they have to enjoy some symmetry properties. In particular, in dimension 2, they are all regular polygons. In dimension 3, regular polytopes. In higher dimension, I mean, this complicated condition, but is yes in a restricted class. And in 20 seconds, how we do it. So just take your minimizer E gamma for a specific gamma and compare its energy with respect to the one of the bowl shape. Well, this is just the fact that E gamma is a minimizer. The non-local energy is Lipschitz with respect to the symmetric difference of sets. And you can bound from below the difference of the perimeters with the, there should be a square. Yes, there should be a square, damn it. Yeah, so that's the square of the symmetric difference between E gamma and WC. And what we prove is that this upper bound can be made quadratic. Of course, you notice that there has to be a square also on the other side, because otherwise it doesn't make any sense. And if you have squares on the two sides, you cancel them, and you see that this inequality is possible only for small values of gamma. And this is basically how we proved it, basing basically our work on an important work of Figali and Maggi. Yes, okay. So that's it. So just to recap very quickly what we talked about non-local energy that are generalization of risk potentials. And we know that for general sets, the only solution is the ball, and we consider the same energy restricted in a class of polygons, and for which regular n-gons are the only critical points for n is equal to 3 and 4, and they are only maximizer, only critical points. And then we talk about this generalization of non-local isoperimetric problem with anisotropic perimeter. And for which, for crystalline norms, we can prove that the wool shape is the only minimizers for small gammas. And with this, thank you for your attention.
Thank you, Riccardo. Are there any questions or comments? If so, please feel free to unmute yourselves and ask.
Can I ask a question?
Yes, please do.
Riccardo, hey. So in 3D, what are the conjectures? Because you don't have regular polygons in the same way.
We don't know exactly, because for the platonic solids, you expect something to be regular. In the other cases, as far as I know, there is not really a conjecture, but you might think about what happens, for instance, for pyramids. Like if you have 4 vertices, you expect it to be, right, but it's a platonic solid. If you have 5, I honestly don't know.
Yeah, I guess for the 5 platonic solids, it could be the regular, but I wonder what it would be if your number of faces isn't consistent.
Should be the closest to a ball as possible, kind of. Because the idea is that if you're a ball, you're good. If you're not a ball, try to be a ball. But to be honest, I mean, my geometry is too weak to tell you in any shape what is the closest one to a ball.
Mine too. Okay, thanks. Yeah, very nice talk.
Lorena, you have a question?
Hi, Riccardo. Thank you so much for your talk. I wanted to ask a question about if you have considered adding background potentials to the energy you're working with, and if you think that adding a background potential would change any of the results you have.
Okay. Interesting. Yeah, what will happen? Background potential.
Because I imagine with the geometry you're working with, I guess depending on the potential you add.
Yes, I mean, 2 seconds answer, probably is wrong, is that, okay, if you have symmetries of inner potential, maybe those are reflected in the, also in the maximizers. Because, the fact is that the kernel in the local energy is symmetric with respect to rotation, and that's basically the good discrete symmetry that you have for maximizer. If you have a background potential that has similar symmetries,